Now, this one's a little bit different. And you're going to get several formulas that you'll be able to use. And those are formulas you will get for the provincial exam as well. And I'll show you what they look like a little bit later, okay, after we get into this unit. But basically, this unit is showing how some trig expressions equal some others because of certain formulas. So we're going to spend a lot of time proving one trig expression equals another using formulas and the knowledge we've gained about trig so far. And a lot of those expressions are going to be in fraction form. And in fraction form, remember, you don't have to write this down. But last year we talked about algebraic fractions, right? Where there was a variable somewhere in the fraction. Could have been above or in the numerator, could have been in the denominator. It could have been in both, okay? And we talked about something called non-permissible values. I can never divide by what? What number can I never divide by? I will get an undefined answer. 0. What value of x would make this expression 0? -4. So we would say, I can use this expression. I can use it for whatever I want, as long as it's not -4. X is not -4. So I could write it 2 ways. And we talked about this last year. I could say the non-permissible value, that's what NPV stands for, is -4, or x can't be -4. The same applies to trig equations. If we have, and this is an example of an identity right here. This is an example of 2 trig expressions that equal each other. Remember, to find the tan, we always divide y by x. Well, isn't y sine? And isn't x cosine? So therefore, tan will be always sine divided by cosine. Okay? That's an identity. That's showing that one expression is equivalent to another. I can use this expression as long as this is never 0. Okay? Cos x cannot be 0. Because I can't do it then. Well, what value of x makes cos x 0? Well, think about it. It's a trig equation that we've used the unit circle. What values of x is, or what angles make the cos equal to 0? In other words, on the unit circle, where is x 0? Well, up at 0, 1, and down here. And let's go radians, because that's what it asks. Pi over 2 and 3 pi over 2. So therefore, I would say the non-permissible values, this is the long way to write it, are pi over 2 and 3 pi over 2. So you could write it like that. Or you could write it like this. X cannot equal pi over 2 and 3 pi over 2. Okay? So you might be given, you know, like you might be given some expression. You know, it could be something like, you don't have to write this down, you know, 1 over sine x, and ask, so for what values of x is this undefined? Okay, and then that's how we would do it. We would set this equal to 0, find the answers, And those are our non-permissible values. So a trig, just to fill this in, when I talked about a trig identity, it's a trig equation like this that is true for all values except the non-permissible values. So this is an identity, it's an equation made up of two expressions. And it's a true identity, this does equal this, as long as x is never these angles. Okay. So that's the first thing we've got to think about when we tackle these identities. Sometimes there will be non-permissible values. You won't be asked that a lot. Okay. What we'll be doing past this will be much more common. And that's proving identities are true. Well, there's a couple ways you could prove identities are true. You could use a series of formulas, which we'll talk about later on. Okay. Or you could do it numerically. So we're taking this equation. This is the identity that we're dealing with. And we're asked, okay, if theta is 60 degrees, show me that this side equals this side. So let's do that one. And here's how we set it up. Here's how we set up proving one side equals the other. First of all, we have a left side and a right side. And in the left side, we've got tan x. On the right side, we've got sine x over cos x. So I'm asked to plug 60 in for x. So I'm asked to find the tan of 60 degrees. Well, how do we find tan 60 again? Don't we just go y divide x and then whatever the unit or whatever the coordinate is on the unit circle that corresponds with 60 degrees? Where is 60 degrees? Up here, right? What's the coordinate? And it's up high like that? 1/2 root 3 over 2. So I'm going to do root 3 over 2 divide 1/2, which is the same as root 3 over 2 times 2 over 1. The 2 on top and 2 on the bottom reduce each other down to 1. And I'm left with root 3 over 1, which is root 3. So that means that if I plug 60 degrees in here and divide this by this, I should get root 3. Well, sine of 60 degrees, divide the cos of 60 degrees. Well, what's the sine of 60? Well, we go back up to 60 and go to the y coordinate, right? Root 3 over 2 divided by the x coordinate at 60 degrees on the unit circle. 1/2. Notice it's the same that we did here. So root 3, I mean, it's the same here, so we know we're going to get the same answer. So we proved it. It works for 60 degrees. So I could say, yes, the left side equals the right side. We're good. But does it work for every angle? Ideally, it should. But let's try another angle and see if it works again. This time, instead of a degree, we're going to do a radian. So on the left side, which is tan x, we're going to find tan of pi over 4. What point on the unit circle corresponds to pi over 4? Should be knowing these by now. Pi over 4? It's in the middle. What's what? No, the point on the unit circle. Root 2 over 2 comma root 2 over 2. So it's y divide x and root 2 over 2 divide root 2 over 2. Well, I don't have to change it to multiplication because anything divide itself is just going to be 1. So that means when I do the sine of pi over 4 divided by the cosine of pi over 4, it should give me 1. Need me to hold that? What's the sine of pi over 4? Root 2 over 2. Divided by the cosine of pi over 4. Root 2 over 2. It's the same division as on the left side, equals 1. So it works for pi over 4. So the left side equals the right side. So we proved it for 2 angles. And what will happen is it will work for every angle as long as it's not pi over 2 and 3 pi over 2. Why? Because those are the non-permissible values we found above. Okay. So that's sort of proving numerically by plugging an angle in and testing to see if the left side equals the right, and taking into account non-permissible values. What we're really going to get into after here is things like this. And I know they look a little complicated to begin with. But if I said like these ones, this is going to be a big chunk of what we do. We're not going to do these yet because we don't have we're not ready to. But notice I want to prove cotangent x plus tangent x is the same thing as cosecant x times secant x. Okay? We're going to use our knowledge of trig and our formulas to prove that one side equals the other. We're not going to pick angles and plug them in because we'd be doing that forever. Okay? Just because it works for one angle doesn't mean it's going to work for every angle. So to do stuff like this, and notice this one's even a little bit more complicated. Okay? It's involving like fractions and things like that. We got to review some algebra, which is what we're going to do here. We got to review how to divide algebraic fractions, how to add and subtract algebraic fractions, things like that. Because instead of the variables, we're going to start plugging in things like sine and cos. So if we remember how to do it algebraically, we'll be able to do this. And this is going to help us prove identities. So when we divide, like here, we're just dividing. Whenever we divide 2 fractions, we change it to multiplication. And then we try to reduce before we multiply. Well, here, I can reduce the 4 and 2 by dividing each by 2. So what do I get? 2 root 3 over 1, which is just 2 root 3. We've been doing that, like we've been doing that in grade 11. We've been doing that this year. Okay. Last year we did ones like this where they were variables. But remember, dividing, you just multiply by the reciprocal. Anything I can reduce? The x's. Those go down to 1 and 1, technically. Because remember, x divided x is 1. So technically it's that. Can't do any more reducing, so what's my answer? That over 1. What happens if we throw some trig expressions? Nothing changes. If we're dividing into trig fractions, change it to multiplication. Sine theta over cos theta, the original fraction, times the reciprocal. Like so, right? Anything I can reduce? No, because remember, to reduce, sine has to be on the top and bottom of either fraction, or cosine has to be on the top and bottom. So what's sine theta times sine theta? What's anything times itself? Well, it's squared. But using trig, we always put that squared after the sine. So it's going to look like sine squared theta. The reason is if we put the squared here, that could get confusing because it means maybe we take the angle and square it before we do sine. That's why we put the squared in front. Over cosine squared theta. That's it. That's as far as you can go. Adding and subtracting algebraic fractions. Well, how do I add fractions? I find common denominators, don't I? What's the lowest common denominator of x and y? Do you remember? xy. Because for the lowest common denominator, it's got to have an x for this to go into it, and it's got to have a y for this to go into it. So it's going to be x times y. So what if I multiply the first fraction by to get xy and y? And whatever you do at the bottom, you got to do at the top. So y times x is xy, y times 3 is 3y. What do I have to multiply the second fraction by to get that LCD? X. So y times x is xy, 2 times x is 2x. And then just to finish the question, since they have common denominators now, I could write one single fraction, but I can't combine 3y minus 2x. They're not like terms. So that's the furthest I can go. So we got to think of that when we do ones with trig. And actually, we can always do it like this. We don't have to split it up into 2 separate fractions. We could make it a single one with the LCD here. What is the lowest common denominator of cos? It has to have a cosine and it has to have a sine. Don't overthink. Cos theta, sine theta. I just multiply the 2 denominators. What must I multiply the first fraction by to get the LCD? Yeah. I'm going to multiply by a sine theta here to get the LCD, which means I got to do the top by sine theta. And what's sine theta times 1? 1 sine theta or sine theta. What do I have to multiply the second fraction by? Cos. Top and bottom to get the LCD. So that gives me cosine on the bottom. Remember, sine cos is the same as cosine. And what's cos times cos? Cos theta times cos theta? Cos squared theta. Done. I made it into a single fraction. What about if we have lots of fractions going on, like a combination of the two? We're adding and subtracting fractions and we're throwing some dividing in there. Well, we've got a fair number of steps to do here. I've got to add the fractions up top by making common denominators. I've got to subtract the fractions on the bottom by making common denominators. And then I got to divide those two answers to get a single fraction answer. So up top, what is the lowest common denominator of y and x? xy or yx. What must I multiply this one by? X. And this one? Y. So when I multiply the numerators, I get x times x, which is x squared, plus y times y, which is y squared. Those are not like terms, so that's as far as I go on the top. On the bottom, what's the lowest common denominator of xy? Well, it turns out to be the same thing. What must I multiply this one by? Y, top and bottom. And this one? X, top and bottom. So, I've already got my LCD, so y times 1 is y, minus x times x is x squared. Okay, so I've made the fractions up top and the bottom as simple as I can. So the next step is to go to division, which means I have to take the top fraction, multiplied by the reciprocal of the bottom fraction. And cancel out any common expressions that appear up top and on the bottom. What can I cancel out? The x. What? X squared. No, because remember, you have to think that's in parentheses. That's in parentheses. These are not the same. You can't take part of this and cancel it with part of that. It's impossible. The only thing I can cancel are the xy's. And those will reduce down to 1. So my final answer is going to be the expression x squared plus y squared, thinking of parentheses around it, divided by y minus x squared. That's as far as I can go. Using this sort of as a template, see if you can do G. It's very similar to the previous one, but instead of x's and y's and numbers, we're using sine and cos. But the method is still the same. So you need to find common denominators up top, make it a single fraction. Common denominators for the bottom, make it a single fraction. Divide, reduce what you can to get your simplified answer. Okay, so what's the lowest common denominator up top? cos theta, sine theta, or sine theta, cos theta, both are correct. So I've got to multiply these. First one by cos theta over cos theta. Second one, sine theta over sine theta. And that's going to give me, yeah, cos theta minus sine squared theta. Good. So on the bottom, LCD is going to be the same, cos theta theta or sine theta cos theta. First fraction on the bottom has to get multiplied by sine theta, top and bottom. Second fraction has to get multiplied by cos theta, top and bottom. And what does that give me in this numerator on the bottom of the big fraction? Yeah. And now we change it to a multiplication. So it's going to be cos theta minus sine squared theta over sine theta cos theta, multiplied by the reciprocal of the bottom fraction. So it's going to be sine theta cos theta over sine squared theta plus cos squared theta. Remember, think of these like they're in parentheses. There's two terms in this one, but they can't be separated. Two terms in this one, but they can't be separated. These are not identical, so I can't cancel them. However, these I can. And I am left with cos theta minus sine squared theta divided by sine squared theta plus cos squared theta. And I am going to stop there for today because it's a good natural break in this lesson. Because the next step is to start analyzing some of these formulas, some of these identities. And just some of them you already know. Like these ones you already know. The cosecant is 1 over the sine. The secant is 1 over cos. Cotangent is 1 over tan. You know those ones. We talked about them before, but we're going to get into other ones as well.